easy to read because they are quite some difficult theory, but take a look, see what. So here is just a repeat of what I told you. Usually this is called perovskite material. It is it has an oxide. These are the oxygen atom, 6 atoms, but in unit cell is 3 atoms, right? Barium titanate. And then at the same time, you have barium on the corner, and then you have titanate at the middle. These are positive. Now, because of the symmetry issue, it is just like what I showed you just now, the birch, right, up and down. They are not aligned. The charge are not aligned with each other. The negative and positive charge does not align with each other. So if you use electric field, you might try to shift them, right? Try to shift them with some relative motion. Because if I apply, for example, if apply electric field in this direction, your negative charge, the oxide, will try to go down, right? And this positive charge will go up. If I apply a negative electric field, then this one will try to go down, right? And oxygen will try to go up, right? But to go up and down, for these two charges to align, actually the energy is higher. So they need to go through a particular energy to switch the polarization or the dipole moment. Is this okay? Right? It's not difficult to understand. If you look at the energy level, it's just like that. It was here. You need to apply some further larger force so that this can go to this side, or vice versa. Okay, this is the so-called reaction coordinate, right? Maybe this is positive polarization, this is negative polarization, for example. Okay, or maybe let me say, for example, this is barium on top, right? This is barium at the bottom of the oxygen, for example, right? Okay, and that's why you get this field. This is called the critical electric field that you need to go over zero polarization. Eventually it's saturated, right? You still have more set polarization, but that's not as much as what we have due to this ferroelectric material, right? Your oxygen, your oxide, silicon dioxide has polarization. We discussed earlier. Helium dioxide has larger polarization, but this one has even larger. So this one, after this, you do have more shifting, but not as much as this shifting. So it's kind of saturated. And then when you come here, even at zero electric field, you have polarization. We call it remnant polarization, something left over. Okay, and that's why you have this. Any questions? Okay, so have this idea, right? We talked about polarization at the beginning. It was not linear. I keep saying negative and positive charge separator. Now it's more than that. When they want to separate, they need to go over this barrier. So suddenly flip. And then when you go back, suddenly flip, right? You see what I mean? Like the birch example, right? The plate, right? You will, but up and down, okay? So that's it. That's all about ferroelectric material. But we need to learn the equation in order to explain that. This equation you don't need to learn, but I need to tell you because this is the class, right? The advanced device physics class. You don't need to know that, but you need to know the people. Landau, he's a very famous Soviet Union scientist, right? It's just like the God. He had a series of books, 10 volumes. Maybe you know about that. Landau and Lifshitz, 10 volumes, right? And actually, in particular, last time when I taught this class, the student from Vietnam, they are still using this for their textbook. And actually, it's considered too difficult. This textbook nowadays, no people will use it as textbook because it's too difficult. But he is a very famous guy. He has many equations. And every equation has the Landau in front. Later, when we talk about superconductor, we are going to have another equation due to Landau, but with another guy. And there are many Landau something equation. So LK equation is trying to tell how the ferroelectric behaves. You just say that, right? You don't have to memorize, but I need to show you what's going on. And probably you only use it one time for this class. Why I want to show this one is to let you know that, hey, just like the drift diffusion equation, right? Partial polarization, right? This is the polarization. The rate of change of polarization is the divergence of the free energy. U is the free energy. Maybe you don't understand what it is. That is okay. Just energy. Okay. And he proposed the U equals to alpha P cube. Square plus beta P fourth plus gamma P6 minus E dot P. E is the external electric field, right? So this is just the energy. We did not discuss the energy of a dipole moment in electric field. And if we discuss, it's just E dot P, right? So that's why you have the energy due to this. But here also show polarization itself has some energy, right? And our goal is to find the minimum energy. So we substitute 2 into 1, right? You can forget this equation, but I want to show you one time, right? If you substitute 2 into 1, rho dp dt, then this is the divergence of U, just like differentiation with respect to P. Then you get 2 alpha P plus 4 beta P to the power 3 plus 6 gamma P to the power 5 minus E. Okay? Equals to 0. If we assume steady state, steady state means what? It's not dependent on time. So dp dt equal to 0, right? This is something you always will see when you do device physics. We want to study the steady state. Then you tell us the electric field equals to 2 alpha p plus 4 beta p to the power 3 plus 6 gamma p to the power 5. And this is the, although we simplify, but this is the very famous Landau Khalatnikov equation. So what does it tell you? It tells you the E. It tells you the P. Isn't that is the plot we are interested in? Polarization and the electric field. This one describe how an ferroelectric material behave. E as a function of P. Is that okay? Now you can forget all of this, right? This is for someone who are interested in this. But I hope that at least you can appreciate that the LK equation gives you E equal to something related to P, and the P are all in third order. Why? Because it was in even order in the U. That is some results from the symmetry, right? From thermodynamics, which again, I don't understand, right? But this is just a Taylor expansion. Do you know? Somehow they just come up with a Taylor expansion, and then it works well. Okay. Any questions? Okay, so even you forget this one, that is okay. Now I want to show you from this equation, how do we get negative capacitance? Why this is possible, okay? So let me write down the equation first one more time. E equals to 2 alpha P plus 4 beta P to the power cube plus 6 gamma P to the power 5th, right? odd term, and then even coefficient, and then alpha, beta, gamma. Okay, so our question is, if E equal to 0, what happened? Then we have 2 alpha p plus 4 beta p cubed plus 6 gamma p plus 5 equal to 0. So what is the value of p if E equal to 0? We just solved the equation, right? So this becomes p times 2 alpha plus 4 beta p squared plus 6 gamma p to the power 4 equal to 0. Okay? Now, can you tell me, if alpha larger than 0, how many solutions do I have? Real solution, if alpha equal to 0.
Six.
Which 6? How do you find the solution of this one? What are the solutions? What p can give you 0? That is the question. What p value can give you 0? We kind of forgot all we learned in the middle school. Something times the bracket equal to 0. Then what does it mean? Either of them will be 0, right? So what are the solutions? Isn't that when p equals 0? Elisa, you try to write something? Is p equals 0 a solution? Can you tell me? Anyone? Is p equal to 0 a solution?
Yes.
Yes, right? What else? When alpha is larger than 0, do we still have solution?
Yes.
What solution? Why do you think yes?
If the thing inside the bracket is 0.
Can I find any p so that the thing inside the bracket is 0?
No, because it's all even power.
Yeah, because alpha is positive, right? You cannot find any p that square and then to the power 4 will give you 0. Okay, of course you don't know how to answer because I have not told you. I'm sorry. We assume beta, gamma larger than 0. Right? Assume beta, gamma larger than 0. So of course you don't know what I'm talking about. Sorry for that, right? So it cannot, so this is only have one solution. Okay, but what if alpha is negative? Now p is still one solution, but I can have 2 other solutions. Okay, so if you try to plot the curve E versus P, if this is P, alpha is larger than 0, you only have this solution. This is a regular dielectric. Right? You only have one P that will give you 0 E. Only one P. Okay? But otherwise, now I swap the coordinate a little bit, right? You will get something like this. You have 3 solutions. One is 0. 0, when P equals 0, it gives you 0 E. Another is P equal to actually the remnant field and negative remnant field. it will give you 0 E also. And that is how you get the negative capacitance, this part. So Landau showed that if you have a negative alpha, then you have a higher chance to get this negative capacitance. Is that okay? If we try to look at the energy, let's look at it again. The energy is given by alpha p squared plus beta p4 plus gamma p6 when E equals to 0. We just look at E equal to 0. At E equal to 0 point, if alpha is positive, you basically only have this solution, this well, as a function of P, right? Because alpha is positive, beta, gamma are positive. Then you change P, you only have a well like this. So it's only possible for you to stay at P equal to 0. But if your alpha can be negative, then you will get a solution like this. This is P, this is U. And this is exactly the P remnant field and the PR here. And you see that this one is not stable, right? If you really want to get negative capacitance, you need to operate at this point. You need to stay at this point. But this point has positive feedback. It is really not stable. So you cannot operate with negative cap. Okay? And that goes back to what we discussed earlier. You cannot, unless you do something, have something in parallel with another capacitance, so the total capacitance is larger than 0. Okay? But we won't discuss this. Right? So why I spend time to go over all this, that is because if you want to go to ferroelectric area, these are the problems you always will see. People keep discussing this. So I want you to understand that in reality, a standalone ferroelectric material, you can only see this curve. Okay, no negative capacitance. And theoretically, you see that these 2 points are stable, but not this point. If you want to go through this point, you need to stay here in order to do the capacitance. It is not stable. Landau theory tells us this already. And also for ferroelectric capacitance, you need a large alpha, negative alpha. Otherwise, you just have a regular capacitor. Okay? I don't expect you to memorize this equation, right? So Landau equation, good to copy in the cheat sheet, but understand this shape will be good, okay? Okay, so we talk about this theory. Again, we need to use it. So how is it going to be useful? Now we do negative capacitance. This is a simulation paper. It showed that in the future, that was 2 years ago, it said, or 3 years ago, actually, yeah. IEDM is a very important conference in device area, International Electronic Device Meeting. It is held now every year in San Francisco. In the past, it's alternatively between Washington and San Francisco. But now they moved to San Francisco because they claim that they get more and more Asian paper, right? So they want to make it easier for those people from Asia. So there are lots of geographic issue there also, right? But that is the very important conference, the most prestigious conference in device. Now, so this paper, it tried to do simulation. This is a FinFET. And in this FinFET, it has the gate oxide, and then you put ferroelectric material here. So ITRS is the roadmap I mentioned to you in the first or second class. And he said that we don't know how to scale the transistor down to 2 nanometer. Here he said that if we use the ferroelectric FinFET, we can scale down to there. But again, this is just simulation, okay? It's good to learn what they did, but don't trust on and don't bet on their paper, right? Especially for conference paper. Even when conference paper, even this is a difficult conference, more difficult than a journal paper, but it doesn't mean that the content are completely correct. Because in conference, it either accept or not. Reviewer is not going to tell you what's wrong and you need to explain. In journal paper, you need to explain everything suspicious or wrong. Here, conference, it looks good, overall great, attract people, then they will accept it. You might actually make some mistake, right? So what do they find? This is a regular FinFET at different technology node. When it becomes very short, of course, this is not exactly the gate length, but in the small technology node, you see this lots of leakage, right? Due to short channel effect. If they use the negative capacitance, they are able to bring it down just because they have smaller subthreshold slope. Let's look at another graph, short channel effect. The red one is the negative capacitance, negative capacitance FinFET, right? When we go to smaller technology node, I-off will increase, but it is always smaller than the FinFET, okay? And then if you look at the threshold voltage, what is this? Do you remember what's the meaning of the threshold voltage going down when you make the transistor shorter? What do we call this? We just learned it. And say again?
VTH roll-off?
Yeah, short channel effect, right? And then for different voltage, solid versus the open symbol, there are different VDS. We have lower VTH when you have VDD. This type of difference is called what? What do we call it? This type of short channel effect?
Dibble.
Dibble, yes. So you see that for negative capacitance, it has less short channel effect. It also has less dibble. Okay. Subthreshold slope, it can control very well. Now you see that it actually did not go beyond 60 millivolt per decade. And this is related to how you design the device. Actually, my opinion, my very personal opinion, ferroelectric is very useful to help you to bring it to very close to ideal slope. But it's very difficult to go below 60 millivolt per decade. People already achieve it, but the range is very small, right? And also not very impressive in my opinion. But if you have a lousy device, it really can help you to stay close to 60 millivolt per decade. And I think this is the most important use. Again, my very personal opinion, okay? Now, the last one I want to mention is so-called drain-induced barrier rising. We have been talking about dipole, drain-induced barrier lowering. When you increase the drain voltage, your threshold voltage reduces, right? But with this ferroelectric material, if you try to look at the internal voltage here, when I increase the drain voltage, actually the voltage here is going to reduce. Think about if I increase the drain voltage, I actually try to pull down the band more. But this is different, opposite. Let's look at this. This is the band diagram. This is a regular device, no ferroelectric layer. When VDS is 0.1, I have this black line. When I keep increasing the VD, this keep going down. You see there's a drain-induced barrier lowering, right? Dipole. So I actually have higher currents and that's why you have lower VTH. But when you use ferroelectric in the simulation and actually in my experience, they confirm, you actually have opposite drain-induced barrier rising. This again, just because of the feedback, negative feedback effect. Okay, we won't go into details, but just hope you aware of this. And the last thing is that you can have hysteresis even in your IV curve if you don't do it right. And this is expected because for ferroelectric material, we do have hysteresis, right? Okay, so I'm over time, but that is all I want to talk about. Thank you very much.